Vector analysis. Hello everyone, my name is Rafael. I'm an electrical engineer, and in this video I would like to invite you to have a conversation with me on vector analysis. In this video we will cover the fundamentals of vector algebra, paying special attention to the dot and the cross products, and comprehend how the conversion from Cartesian to cylindrical and spherical coordinates is carried out. To finish, in order to consolidate our understanding, we will solve 4 exercises. Let's go. A scalar quantity has magnitude but no direction. Examples of scalar quantities include mass, temperature, and time. A vector quantity has both magnitude and direction, and examples of vector quantities are velocity and force. Consider vectors A and B. Z, which represents the sum of A and B, is obtained by beginning the second vector from the head of the first and completing the triangle. We are going to specify vector addition when we analyze the Cartesian coordinate system. Let's pay attention to the commutative law. Observe that A plus B is equal to B plus A, and they produce both vector Z equally. The associative law, A plus B plus C is equal to A plus B plus C. Okay? This is the associative law. And the subtraction, how do we understand subtraction? The rule for subtraction of vectors follows that for addition. For we may interpret A minus B as A plus the opposite of B, signifying that we are adding one with the opposite of the other. Now, scalar multiplication. When a vector is multiplied by a scalar, its magnitude changes, but its direction does not when the scalar is positive. When you multiply a vector by a positive scalar, its magnitude changes, but its direction does not. However, when you multiply a vector by a negative scalar, both its magnitude and its direction changes. Okay? The direction is reversed. Now let's see this. R and S are scalars, while A and B are vectors. We are going to multiply scalars by vectors. And this is done using both the commutative and the distributive laws. The associative and distributive laws. R plus S times A plus B is equal to R times A plus B plus S times A plus B. And this results in R times A plus R times B plus S times A plus S times B. Okay? This is how scalar multiplication of a vector is carried out. And the equality of vectors. Two vectors are said to be equal if their subtraction produces the zero vector. Okay? A plus the negative of B, or the opposite of B, has to produce vector 0. Otherwise, they are not equal. Okay, this is the condition for equality. Now let's take a look at the Cartesian coordinate system. The simplest method for representing vector lengths, directions, angles, and components is by means of the Cartesian coordinate system. To describe a vector in the Cartesian coordinate system, we can use unit vectors. In this way, AX is the unit vector in the x direction. AY is the unit vector in the y direction, and AZ is the unit vector in the z direction. In such a representation, vector r is represented as 2 times ax plus 3 times ay plus 2 times az. Now let's take a look at vector addition and subtraction using the Cartesian coordinate system. A vector rp pointing from the origin to point P is written as 1 in the x direction plus 2 in the y direction plus 3 in the z direction. Likewise, vector rq pointing from the origin to point Q is written as 2 in the x direction minus 2 in the y direction plus 1 in the z direction, and the vector RPQ, this vector here, from point P to point Q, is obtained from the difference R PQ is equal to RQ minus RP. And in this way, we simply subtract the vectors. It is going to be AX plus 2AY plus 3 AZ minus 2AX minus 2AY plus AZ. Subtracting, we reach that RPQ is AX minus 4AY minus 2AZ. Okay? This is how we represent vectors from the origin to the point, and subtracting one vector by the other. This vector here is from point P to point Q, and the vector RPQ can be obtained from the subtraction RQ minus RP. Now let's consider components and directions. In physics, vectors point in the direction of a force or a field, and they may be expressed by their components in the x, y, and z directions. Let's understand let F be a force vector. It may be expressed in Cartesian coordinates as F is equal to Fx in the x direction plus Fy in the y direction plus Fz in the z direction, in which Fx, Fy, and Fz are the components of F in the x, y, and z directions respectively, and the magnitude. How do we compute the magnitude of a vector? The magnitude of a vector can be obtained from its components as the magnitude of vector F is going to be the square root of Fx squared plus Fy squared plus Fz squared. This is the magnitude of the vector, and the direction can be obtained in such a manner let's take a look at the Cartesian coordinate system. You want a vector such as this. Okay, this is our vector, and this vector has a direction, and there will be a unit vector here. This is vector F, and this is the unit vector AF. Okay, this unit vector points in the direction of the vector, and this unit vector can be expressed as if F is equal to the magnitude of F in the direction of the vector. Okay, you see that AX, AY, and AZ are unit vectors, but AX is in the direction of X, AY is in the direction of Y, and AZ in the direction of Z. AF is different. AF is not in the direction of X or Y or Z. AF is the unit vector in the direction of this vector here, okay? And this vector can be expressed in this way, okay? As a composite in X, Y, and Z, but also in its own direction, okay? So, in this alternative way of expressing, we compute the magnitude first, and then the direction of the vector, and the direction of the vector AF is obtained by dividing the very vector by its magnitude. Alright? So this is the magnitude and this is the direction of the vector. Now let's consider an example. Example number 1. Specify the vector extending from the origin towards point G. Point G, 2, -2, and 1. We want to specify the vector extending from the origin to point G, 2, -2, and 1. Okay? Let's call the vector from the origin to point G simply vector G. Vector G can be written in two ways, okay? The first way, letter A first, we are going to specify it in terms of x, y, and z. Okay? So, in using x, y, and z components, G is expressed as 2 in the x direction minus 2 in the y direction plus 1 in the z direction. This is the first way of specifying this vector. And the second we just saw, we write it in terms of the magnitude and the direction. G equal to the magnitude of G times AG. AG is not in the x direction or in the y direction or in the z direction. AG is in the direction of the very vector. Okay? Let's compute the magnitude. The magnitude of G is the square root of 2 squared plus -2 squared plus 1 squared. And this is equal to 3. And how about the direction? The direction, the unit vector in the direction of the vector is AG is equal, simply pass this dividing here, G divided by the magnitude of G, and this is equal to, if the magnitude is 3, then it is going to be 1/3 of 2ax minus 2ay plus az. Okay? And now we want to compute it in this way. Okay? Magnitude times the direction. Then we express G as the magnitude, 3, okay, the magnitude, now the direction, 2/3 of ax minus 2/3 in the y direction plus 1/3 in the z direction. Okay? This is an alternative way of expressing the vector. This is expressed in x, y, and z, okay, taking directly from the coordinates of the point, and here expressed in magnitude and its own direction. The magnitude is 3 and the direction of the vector is this, okay? This is how we express vectors using the Cartesian coordinate system. Now, let's consider vector multiplication and dive deep into the dot and the cross products. The dot product giving two vectors A and B. The dot product between them is the product of the magnitudes and the cosine of the angle between them. A dot B is equal to the product of the magnitudes of the vectors, the magnitude of A times the magnitude of B times the cosine of the angle between them, between the vectors. Now let's describe the vectors in the Cartesian coordinate system. If A is AX in the x direction plus AY in the y direction plus AZ in the z direction, and if B in a similar way is BX in the x direction plus BZ BY in the y direction plus BZ in the z direction. We want to compute the dot product between them. A dot B will be equal to AX in the x direction plus AY in the y direction plus AZ in the z direction in a dot product with BX in the x direction plus BY in the y direction plus BZ in the z direction. What we want to do now is to calculate. Okay? We are going to apply the distributive law here, and we're going to get AX BX AX AX, okay? This multiplying this. Now we do the same, this multiplying this. ax by ax in a dot product with ay, and we compute now this times this, ax bz, ax in a dot product with az, and so on until we get this. This with this, we're gonna do this with this, this with this, this with this, and this with this, this with this, and this with this, and in the end we reach AZ BZ in a dot product with AZ in a dot product with AZ. Okay? And we need to bear in mind that as it is a cosine, you see that x is here, y is here, and z is here. The cosine between them, the angle between them is 90 degrees. So the cosine of 90 degrees is 0. Okay? And what do we infer from this? We understand that AX in a dot product with AY is equal to AY in a dot product with AX. If we change the position, it's going to be the same. It is equal to 0, which is the same as AX in a dot product with AZ. If we do AZ dot AX, change the position, won't change the result. And it is also equal to AY in a dot product with AZ. And this is equal to 0 because the cosine of the angle between them is 90 degrees. And we know that the cosine of 90 degrees is 0. In a similar way, AX dot AX is equal to AY dot AY, which is equal to AZ dot AZ. And this is equal to 1 because the cosine AX is here. Let's suppose that AX is here. Okay, AX. AX with AX, the angle between them is 0 degrees. And the cosine of 0 degrees is 1. Okay, then the dot product between AX and AX, AY and AY, and AZ and AZ is 1. That's the reason. Okay? In this way, alternatively, this is one way of doing this. Alternatively, we can write the dot product as A dot B is equal to AX BX plus AY BY plus AZ BZ. Okay? This is the result that we get when we develop this product here, written in the Cartesian coordinate system. Alright? The direction, one of the most important applications of the dot product is that of finding the component of a vector in a given direction. Okay? How do we find the component of a vector in a given direction? here is y, here is x, and here is the vector. We want to find the component of the vector in the x direction. How do we do it? The component of vector b, the component of vector b in the x direction can be easily found by applying the dot product. Okay, bx is a scalar. Okay, I don't know if you noticed it. If you didn't, I shall mention it to you. The dot product is a multiplication. The cross product is a multiplication too. Okay, they are vector multiplications. What is the difference? The result of the dot product is a scalar. Okay, it is a number, not a vector. If you compute the dot product between two vectors, you're gonna find a scalar, a number. And the cross product, you're gonna see the cross product subsequently, and you're gonna see that the result of the cross product is a vector. They are both multiplications of vectors. You see here the multiplication, but the result of the dot product is a scalar, and the result of the cross product is a vector. So this is a number, not a vector. Okay, bx is equal to the magnitude is equal to vector b in a dot product with the unit vector in the x direction. Okay, the number, not a vector, the number bx is the result of the dot product between vector b and the unit vector in the x direction. Okay, and this is going to be the magnitude of b times the magnitude of ax. We know that the magnitude of ax is 1 because ax is a unit vector, times the cosine of the angle between them, and in this way it is simply the magnitude of b times the cosine of the angle. Alright? This is how we find. Okay? This is easy to understand because if you remember geometry, your high school geometry, you're going to see that this is a right triangle, and the magnitude of the vector is the hypotenuse of this right triangle. Okay? So this side here is the hypotenuse times the cosine of the angle. Alright? This is how you learned this in high school. And I'm just showing you in a different way using the dot product. Okay? Now let's solve an exercise. Example number 2. Consider the vector field G equal to y in the x direction minus 2.5x in the y direction plus 3 in the z direction, and at the point Q, 4, 5, and 2. Find in letter A. Letter A, find G at Q. Okay? G at Q. This is a vector field. Any kind of vector field. It could be a magnetic field, for example, or an electric field. It is described by this vector equation here. We want to find the G at Q. How do we do it? We simply substitute the coordinates of point Q into the expression of the vector field. G at Q is going to then be G at Q expressed by this vector. Okay, we put 5 here, then it is 5 in the x direction. We put 4 here in the place of x, and it produces a -10 in the y direction, and 3 is a constant here in the x in the z direction. Then it is going to only be simply 3 in the z direction. Now let's consider letter B. Letter B, the scalar component of G at Q in the direction of the unit vector an equal to 1/3 of 2ax plus ay minus 2 times az. We want to compute the scalar component of G at Q. The scalar component of G at Q. We're not working with this anymore. We're working with G at Q now. We want the scalar component of G at Q in the direction of this unit vector. And to find the scalar component of G at Q in the direction of this unit vector, we use the dot product, okay? In a similar way as I did here, it is going to be the dot product between this G at Q in a dot product with the unit vector, this unit vector here. So we are going to simply multiply them, but not a simple multiplication. We need to consider the directions, and to do this we are going to use the dot product. It's going to be 5ax minus 10ay plus 3az times this, or in a dot product with 1/3 of 2ax plus ay minus 2az. Okay? We know that this with this, ax with ax is 1, because the cosine is 0 of a angle of 0 degrees is 1. But this with this is not, because the angle between ax and ay is 90 degrees, and the cosine of 90 degrees is 0. Then we are going to only multiply this with this, this with this, and this with this, okay? The similar directions. Then it is going to be 5 times 2/3 plus -10 times a third plus 3 times negative 2/3. And this is equal to negative 2. This is the result of letter B. Now let's go to letter C. What does letter C want? Letter C, I'm going to put letter C here. The vector component of G at Q in the direction of AM. We want the vector component of G at Q in the direction of AM. The vector component is obtained by multiplying the scalar component by the unit vector in the direction of AM. Okay? The vector component is obtained by multiplying the scalar component by the unit vector in the direction of AM. This is the scalar component, okay? This is the result of this dot product. If we multiply this by this, we have the vector component, okay? It is going to be G in the direction of this unit vector, okay, and it is going to then be equal to negative 2, okay, times the unit vector, a third of 2ax plus ay minus 2az, and this is equal to negative 4/3 ax minus 2/3 ay plus 4/3 az. And to finish, letter D, the angle theta between G at Q and AM. This unit vector, we want now to calculate the angle between them. The angle between G at Q and the unit vector that we are considering. Okay, we're going to use that the vector, the product of this dot product here produces a number, a scalar, okay? The result of the dot product is a scalar, not a vector, and this is equal to the magnitude of G times the cosine of theta, okay? And let's suppose this here and here. Let's suppose there is a vector here, and the unit vector is pointing in this direction here. Okay, there will be an angle between them. Negative 2 is equal to the magnitude of this. The magnitude of this is the square root of 25 plus 10 squared 100 plus 9 equal times the cosine of theta. Times the cosine of theta. And in this way we find that the cosine of theta, we simply pass this dividing, and the cosine of theta is equal to 99.9 degrees. No, sorry, I made a mistake here. The cosine of theta is equal to this divided by this, okay? This divided by this. And in this way we can calculate theta as the inverse cosine of -2 divided by the square root of 134. And this is equal to 99.9 degrees, okay? And this is all for the dot product. Let's talk about the cross product now. The cross product between vectors A and B is a vector whose magnitude is the product of the magnitudes of A and B and the sine of the angle between them, and whose direction is perpendicular to the plane containing A and B, following the right hand screw, okay? The right hand screw from A to B, then C will be, if the plane containing A and B is the XY plane, okay? The XY plane here, then if X is this and Y is this, Z is going to be this, okay? Z is going to be perpendicular to the plane containing A and B. If they are in this plane here, then the direction of the vector resulting from the cross product is going to be in a perpendicular to the plane of A and B. So if C is the vector resulting from the cross product between A and B, then C will be equal to the magnitude of A times the magnitude of B times the sine of the angle between them. But observe that we need a direction, since the result of the cross product is a vector. The result of the dot product is a scalar, but the result of the cross product is a vector. Then it is going to be in the AN direction, and this direction is normal to the plane. If vectors A and B are in this plane, then the result of the cross product will be perpendicular to this plane. Reversing the order of the cross product results in a unit vector in the opposite direction, okay? So, B cross A is equal to the negative of A cross B, okay? If A cross B points upwards, B cross A points downwards, all right? That's what we conclude from the rule. And observe that AX vector AY is AZ. AY vector AZ is AX. And AZ vector AX is AY. Okay? And observe also that if we reverse this, if we put, okay, follow this rule here. B cross A is the negative of A cross B. So AY cross AX is negative AZ. AZ cross AY is negative AX. AX cross AZ is negative AY, alright? And for unit vectors lying in the same line, such as AX vector AX, AY vector AY, and AZ vector AZ, the sign of the angle is 0. The sign of 0 is 0. Then they are all equal to 0, okay? And in this manner, if we compute A cross B using Cartesian unit vectors, okay, in this way, AX in the x direction plus AY in the y direction plus AZ in the z direction, in a cross product between with B in the x direction plus B in the BX in the x direction, BY in the y direction, plus BZ in the z direction. If we compute this cross product, we find that it is a vector, of course. The result of the cross product is a vector. It is going to be a vector of the kind AY BZ minus AZ BY in the x direction plus AZ BX minus AX BZ in the y direction plus AX BY minus AY BX in the z direction. Okay, this is the result. Okay, vector C obtained from the cross product between A and B is this. Okay, the coordinates of C will be CX will be AY BZ minus AZ BY, CY will be AZBX minus AXBZ, and the CZ will be AXBY minus AYBX. Okay? This can be written as a determinant. Okay? A cross B can be written as a determinant in this way: AX, AY, and AZ, AX, BX, AY, BY, and AZ, BZ. Okay? we can memorize all this instead of memorizing this in this way. There is an easier way of memorizing this, and we use this determinant to memorize the way we calculate the cross product. Now let's consider an example. Example number 3. Find the cross product between vectors A and B. Vector A is this and vector B is this. And the solution is going to be, to find the cross product, we use the rule of Sahri. Okay? And what is the rule of Sahri? The rule of Sahri is this: A cross B will be equal to A in the x direction, A in the y direction, and A in the z direction. Below here we put AX. AX is 2. And below AX we put BX, and BX is -4. Below AY we put A in the y direction, which is -3. And the same for B, which is -2. The same we do for the z direction. For A is 1 and for B is 5. To use the rule of Sahri, we repeat the first two columns. AX to -4, AY -3 and -2. Okay? Now we follow the multiplications guided by these arrows here. This, and this. These arrows here will be multiplied by -1. And these arrows here, the sign stays the same. Positive, positive, and positive. In this way, A cross B will be equal to -1 times this product here, which is 12 in the z direction, this product here, which is -2 in the x direction, and this product here, which is 10 in the y direction. Now this product here will be -15 in the ax direction, -4 in the y direction, and -4 in the z direction. And thus the cross product between vectors A and B is -13 AX, -14 AY, minus 16 in the z direction. And to find the opposite, okay, the vector in the opposite direction, we simply invert the direction of this vector here. So B cross A is equal to 13 in the x direction plus 14 in the y direction plus 16 in the z direction, okay? And this is all for the cross product. Now, let's consider the conversion from Cartesian to cylindrical and spherical coordinates. Let's understand the conversion from Cartesian to cylindrical coordinates by means of an example. Example number 4. Transform the vector b, y in the x direction minus x in the y direction plus z in the z direction into cylindrical coordinates. Okay, my friends, this is the question. Let's go to the solution. Any vector can be expressed in cylindrical coordinates as A is equal to a rho in the rho direction plus a phi in the a phi direction plus a z in the z direction. Therefore, the new vector b expressed in cylindrical coordinates will have b rho in the rho direction plus b phi in the phi direction plus bz in the z direction. Okay, let's compute firstly b rho. B rho will be equal to b in a dot product with a rho. Okay, remember that the dot product allows us calculate the component of any vector in the direction that we want. We want the rho direction. Then, to express the component of b in the rho direction, we simply use the dot product in this manner here. And this is equal to the vector y in the x direction minus x in the y direction plus z in the z direction in a dot product with the unit vector in the rho direction. And this produces this y ax in a dot product with a rho minus x ay in a dot product with a rho plus z az in a dot product with a rho. Okay? Similarly, we do for bz, which is going to be b phi. B phi first. B phi is the component of b in the phi direction. We learned that we can find this component here in the phi direction, use the dot product in such a way. B in a dot product with the unit vector in the phi direction produces the component of b in the phi direction. We learned this, and it is going to be this, the vector y ax minus x ay plus z az in a dot product with a phi. extending, we find y in a dot multiplying ax in a dot product with a phi minus x ay in a dot product with a phi plus z az in a dot product with a phi. Okay? Now let's understand the question graphically. See the point here, point P. Point P. It has components in the Cartesian coordinate system, and it has components in the cylindrical coordinate system. Okay, you can express vector Vp from the origin to P using Cartesian coordinates and cylindrical coordinates. Using Cartesian coordinates, we have x, y, and z. Okay, Rp is not B. Okay, this is just for example. And in expressing the very vector in cylindrical coordinates, we need ρ. This ρ positions provides the magnitude of the vector in the xy plane. That is this angle here from the x-axis going towards the y-axis. Okay, ρ and phi exist together, they don't exist alone. And to move this upwards or downwards the xy plane, we need z. Okay, that's why a vector expressed in x, y, and z can be expressed as ρ, phi, and z. Okay, ρ, phi locate the vector in the xy plane, and z translates it downwards or upwards the xy plane. Okay, from the graph we can infer that x is equal to ρ times the cosine of phi. Okay, this is a right triangle, and ρ is the hypotenuse of this right triangle. And in this way, the x component is going to be simply the hypotenuse of the right triangle times the cosine of the angle phi. Likewise, we compute y, which is going to be, y is here. Okay, in front of the angle is sine, at the side of the angle cosine. So in front is sine theta, sine phi, and z is equal to z. Okay, z does not change from the Cartesian coordinate system to the cylindrical coordinate system. But what if we have the cylindrical coordinate system and we want to convert to the Cartesian coordinate system? Observe that as ρ is the hypotenuse of this right triangle whose sides is x and y, to find the hypotenuse we use Pythagoras, and then ρ is simply x squared plus y squared, the square root of it all. And how about the angle phi? Remember that the tangent of an angle is that participates in a right triangle is the side in the front divided by the side at the side. Okay? So the tangent of phi is y divided by x. But we don't want the tangent. We want the angle. And to compute the angle having the tangent of the angle, we calculate the inverse tangent. Okay, so phi is the inverse tangent of the tangent. And how do we calculate the tangent? The tangent is y divided by x. What does it mean? It means that phi is the angle whose tangent is y divided by x. Okay? Returning to the exercise and consider that the cosine of phi is equal to the sine of 90 degrees minus phi. Okay? This is right for this. The cosine of this angle is equal to the sine of this angle and vice versa. The cosine of this angle is equal to the sine of this angle. You're going to need to consider this to calculate these dot products here. Okay? Okay. In this way, a rho times ax is equal to the cosine of phi. Pay attention to this, okay? We have here x and x in a dot product with rho is equal to the cosine of phi. A rho, ay with a rho is equal to the sine of phi. A phi with ax is the negative of sine of phi, and a phi with ay is the cosine of phi. And they will be equal to 0 in a dot product with z, because z is pointing out of the plane which they belong. Okay? So there is a non-zero dot product among them all here. There is a non-zero dot product among them, but as z is in this direction, the angle is 90 degrees, the cosine of 90 degrees is 0, and in this way, this is 0, and this is 0, okay? That's why anything in a dot product, anything here in a dot product with z is 0. Alright? In this way, we find that I'm going to erase the here, and I'm going to show you the rest of the solution. In this way, the component of vector b in the whole direction will be y ax a rho minus x ay a rho, and substituting this is equal to the cosine of angle phi, okay? This in a dot product with this, okay? X in a dot product with a rho is the cosine of the angle. Remember the definition of the dot product. So it is equal to y times the cosine of phi minus x times the sine of phi. And y. Why this is the sine and not the cosine? Because this angle here theta, the sine of theta, the cosine of theta is equal to the sine of phi. Okay, remember, see here, phi plus theta is equal to 90 degrees. What does it mean? What is the property that we can use? The cosine of this is equal to the sine of this and vice versa. What we want the cosine of theta, but the cosine of theta is equal to the sine of phi. That's why we use here sine of phi. Alright? Have you guys understood? And using this, that x is rho cosine phi and y is rho sine phi, we can express this in this way. Rho sine phi cosine phi minus rho cosine phi sine phi, and this is equal to 0. So the component of vector b in the rho direction is 0. And how about the component of b in the phi direction? The component of b in the phi direction was expressed as y ax a phi minus x ay a phi. Okay? Ax a phi, the dot product between ax and a phi is the sine of phi. So it is the negative of the sine of phi. Okay? The negative of the sine of phi. And how about this? Ay with a phi. The dot product is the cosine of phi. So it is negative x times the cosine of phi. Substituting these two here, we find that it is equal to negative rho sine squared of phi minus rho cosine squared of phi. And this is equal to negative rho. Okay? And thus, finishing, we express b in cylindrical coordinates as b is equal to negative rho in the a phi direction plus z in the az direction. Observe that z does not change because z it belongs both to the Cartesian and to the cylindrical coordinates. And see that the component in the whole direction is 0. That's why the whole direction doesn't appear here. Okay, this is all for cylindrical coordinates. Let's go to spherical coordinates now. Let's understand now the cylindrical coordinates. Take a look at this point here, point P. It is expressed in cylindrical coordinates by the magnitude of a vector r, this angle here, theta, and this angle phi. Okay? And the vector then that goes from the origin to point P has a magnitude and this angle here that goes in this direction here and this angle that goes in this direction. This angle here in the xy plane and this angle here over the z-axis from the positive to the negative along z. Okay? Let's pay attention to this vector here, vector r. The projection of r in the xy plane, okay? This is the xy plane. The projection of r in the xy plane, this, okay, this here is the projection of r in the xy plane. If we consider the angle theta, observe that this is equal to this, okay? This is equal to this. We need a little bit of geometry to understand. And as it is in front of the angle, then it is r times the sine of the angle. How about this side here along the z direction? It is at the side of the angle, not in front. It is at the side of the angle. Thus, is equal to the vector, or the length of the vector, times the cosine of the angle, okay? But we are more interested in this here below, which is r times the sine of the angle, okay? Understanding this, we can write x and y in terms of the projection as cosine and sine, okay? X is equal to the projection. Let's call the projection any kind of letter. Okay, let's invent tau. Tau. The projection here, okay? This is the projection. The projection of r in the xy plane. And we are calling it tau. X is equal to tau times the cosine of phi. And y is equal to tau times the sine of phi. Okay? Y is in front, is the sine. At the side, it is the cosine. Okay? But we have just seen that the projection, which is also here, okay, the projection which is also up there, can be written tau, which is the projection, can be written as r times the sine of theta, okay? And in this way, x will be expressed as r times the sine of theta times the cosine of phi. In a similar way, y is expressed as r times the sine of theta times the sine of phi. Okay? And how about the z component? The z component is this. Okay? The z component is this here. And it is at the side of theta. Then it is r times the cosine of theta. And this is how we express x, y, and z using spherical coordinates. Now, what if we have the Cartesian and want to convert to spherical? That's a good question, isn't it? That's a good question. Let's remember this tau here, which I'll put here. How do we express tau in terms of x and y? Tau is the hypotenuse of this right triangle here. Okay? And how about r? R is the hypotenuse of this right triangle here. Okay? So, tau is equal to the square root of x squared plus y squared. Did we know? We know everything when we have to calculate on the plane, but we are now studying the space, not the plane anymore. Observe that this is z, okay? This is z. And now r, not tau anymore, tau is on the plane, and r is in space. R is the hypotenuse of the other right triangle. Therefore, r is equal to the square root of tau squared plus z squared. Okay? R is equal to tau squared plus z squared. If we bundle them together, we find that r is equal to the square root of x squared plus y squared plus z squared. And how about the angle theta? Theta, the cosine of theta is z divided by r. The cosine of theta is z divided by r. Then theta is the inverse cosine of z over r, where r is this, okay? In the place of r, you simply put this. And how about phi? Phi we know. Phi is the angle whose tangent is y divided by x. And in this way, phi is equal to the inverse tangent y over x. And in this way, we convert from Cartesian to spherical and from spherical to Cartesian coordinates. Now, to finish our understanding, let's solve an exercise. Exercise number 5 now, I think. Exercise number 5. Exercise number 5. Given a vector field expressed in this way, in the x direction, transform this vector field from Cartesian to spherical coordinates. As we learned, to transform, to find the components of a vector in a given direction, we simply use the dot product, because the dot product produces the component of the vector in the direction we want, okay? And if we want the component of this vector field in the r direction, we are going to multiply it using the dot product in the r direction. And in this way, the component of g in the r direction is going to be g, the very vector, in a dot product with the unit vector in the AR direction, okay? Then it is going to be xz over y multiplying ax with AR. The magnitude of a unit vector is simply 1. We don't have to worry about the magnitude. It's going to provide us only the component in the direction of the unit vector. Okay? And with some manipulation, and knowing that ax with ar is sine theta times the cosine of phi, okay, this is equal to xz over y sine theta times the cosine of phi, okay? You can use a table, and some books provide you a table, okay? I demonstrated to you the dot product between Cartesian coordinates and the cylindrical coordinates. I'm not going to have time here to demonstrate the dot product of Cartesian coordinates with spherical coordinates. If you use a table, you're going to see that ax in a dot product with ar produces this, okay? And with a little bit of manipulation, we find that this is equal to, I'm going to write it here, this is equal to r times sine theta cosine theta cosine squared of phi divided by sine phi. Okay? Similarly, we can compute the component of this vector field in the theta direction. How do we do it? G theta will be equal to the vector in a dot product with the unit vector in the direction we want. And we want the theta direction, then it is going to be a theta. Okay? The dot product is useful because we are multiplying the dot product, both the dot product and the cross product are multiplications. But observe here that I am multiplying by a unit vector. What does it mean? It means that I'm not altering the magnitude. Okay? We are taking into consideration the angle between them. But I am not altering the vector because I am multiplying it by 1. The magnitude of a unit vector is 1. Okay? And this is xz over y ax in a dot product with a theta the dot product between ax and a theta is cosine theta cosine phi xz over y cosine theta cosine phi. Again, I demonstrated for the cylindrical coordinates. I'm not going to demonstrate for spherical coordinates. You simply look it up in a table. And again, with a little bit more of manipulations, we find that this is equal to r times cosine squared of theta cosine squared of phi divided by sine phi. And to finish, we are going to find the component of the vector in the phi direction. G phi is equal to G in a dot product with a phi, and this is equal to xz over y ax a phi, and the dot product of ax with a phi is negative sine phi. Then this is xz over y times minus psi phi. Okay? And manipulating this, okay, observing how do we manipulate this. I'm gonna give you a hint. Substitute, okay, x. We saw that x was equal to r sine theta cosine phi, y equal to r sine theta sine phi, and z equal to r cosine theta. Okay? I'm going to give you this tip to go from here to here, here to here, and from here to the next step. Use this, okay? This is how you are going to substitute. And then we find negative r cosine theta cosine phi. Okay? And collecting the results, we ultimately find that the G is equal to r times the cosine of theta times the cosine of phi sine theta cotangent phi in the AR direction plus cosine theta cotangent phi in the A theta direction minus A phi. Okay? Try yourself in your house, in your office, in your college, and compare your result with me. Okay? And this is all for this exercise. Now let's solve some drill problems that I found using some of my reference textbooks, my friends.